Okay, so you ever, like, feel yourself getting pushed back into your seat when a car takes off really fast?
Oh, yeah.
Or, like, watch a feather just kind of float around in the wind while a baseball drops straight to the ground?
Uh-huh.
It makes you wonder, right? Like, what's really going on there? What actually makes things move the way they do?
Yeah, for sure. What seems really obvious at first can get pretty complex when you look deeper.
Yeah.
And sometimes it's not even what you'd expect.
That's so true. And welcome to the deep dive, where we dig into the sources you send us and break down the important stuff in a fun way.
Exactly.
And today you sent us this physics chapter all about motion. It's pretty cool stuff.
Yeah.
So for you, our listener, we're going to dive into the core of how things move.
That's our mission here. To go beyond just everyday ideas about motion and get to the laws that really control how everything works. We'll be looking at Newton's laws and the big ideas of force, mass, and weight.
Right, the foundations.
Exactly.
And your source is a physics textbook, so we know it's legit, scientifically speaking.
Yeah.
Okay, so the chapter starts with the idea of force. What is a force in this context, anyway?
Well, simply put, a force is a push or a pull. But the key thing, and figure 4.1 in your source shows this nicely, is that a force is always an interaction. It's never just one object doing its own thing.
Oh.
It always involves at least two things, either two different objects acting on each other or an object interacting with its surroundings.
Like a give and take.
Yeah, exactly.
Wow.
So when you kick a ball, it's your foot pushing on the ball. It's not like the ball just decides to move on its own.
Gotcha. And the chapter says force is a vector quantity. What does that even mean?
Okay, so a vector means it's not just about how strong the force is, like how much oomph it has,
Uh-huh.
but it's also about the direction it's going in. Think of kicking that ball again. The direction your foot's pointing is just as important as how hard you kick it.
Right, you wouldn't kick down if you wanted to make a goal.
Exactly.
So then there are contact forces and long-range forces. What's
No.
the difference?
All right, well, contact forces, you guessed it, involve things actually touching each other. Figure 4.2 has some cool examples. There's the normal force. That's the force a surface exerts on an object that's on it. Like if you put your phone on a table,
Right.
the table pushes up on your phone. That's the normal force. And normal here means perpendicular. So it's always at a right angle to the surface.
So if I put my phone flat on the table's pushing up on my phone straight up
Yeah,
at
exactly.
90 degrees.
Exactly, 90 degrees.
Okay.
Then you have friction. That's another contact force. But this one acts like parallel to the surfaces that are touching. And it always tries to stop things from moving or sliding against each other.
Like when I try to slide my phone across the table,
Yeah, you have to push against the friction.
I feel the resistance.
Yeah, exactly. And finally, there's tension. That's the force you get when you pull on something like a rope or a cable or even your muscles. When you lift weights, the tension in the rope is what holds the weight up.
Okay, so those are forces where you can like see or feel things touching. What about long-range forces?
Those are forces that act over a distance without actually needing to touch. Gravity is the one we're all familiar with.
Yeah.
The earth pulls on you and keeps you on the ground,
Yeah.
even though you're not like physically touching the earth in the same way your phone touches the table. Figure 4.22 shows that.
Right.
And your weight is just the amount of that gravitational force.
Magnetism is another long-range force. You know, like magnets attracting or repelling each other
Uh-huh. Without touching.
without touching. Exactly.
Okay, so the chapter talks about the Newton as the unit we use to measure force,
Yeah.
like in the SI system.
Right. It's the standard way we measure how strong a push or pull is. We'll get a better feel for it when we talk about Newton's second law.
Okay.
But for now, just think of it as a way to say how strong a force is. And they mention a spring balance as a tool for measuring force.
Yeah.
You know, like those things you see at the airport for weighing luggage. The more you pull on it, the more the spring stretches, and that tells you how strong the force is. Okay, I get it. So then things get trickier when they talk about the superposition of forces. That sounds kind of complicated.
Yeah, but it's a really useful idea.
Mm.
Basically, if you've got multiple forces all acting on an object at the same time, it's like there's one single force acting on it.
Huh.
And that single force is like the sum of all those individual forces.
Like the total force.
Yeah, total effect. Like imagine a bird flying. It's got gravity pulling it down the lift from its wings, pushing it up, and maybe wind pushing it sideways.
Right.
And how the bird actually moves depends on all those forces combined,
All those forces together.
all together.
Yeah.
That's called the resultant force, or the net force. Figure 4.4 illustrates this principle.
Okay, so you don't just add up the strengths, you have to account for the directions too.
Yeah, exactly. That's where the vector thing comes in.
Okay.
And to figure out this total force, when the forces are all going in different directions, we use vector addition.
Oh, okay.
And the book talks about this component method, which is a way to do that. Equations 4.2 show how you can break down each force into its x, y, and even z components,
Uh-huh.
like along some axes that we choose.
Mm-hmm.
And then you just add up all the x components to get the x component of the total force, and the same for the y and z.
So it's like taking a force that's at an angle and making it into simpler forces along straight lines. They're
It's
easier to add.
exactly. And then equation 4.2 also shows how you could use the Pythagorean theorem
Mhm.
to find the strength of that total force.
Okay, that makes sense. And there's that example with the three wrestlers pulling on a belt.
Oh, yeah.
That's a good visualization. How does this superposition of forces apply there?
It's a perfect example.
Hmm.
Example 4.1 and figure 4.7 show you how it works. You've got three forces each with a different strength and direction. The example breaks each force down into its horizontal and vertical components, then adds up all the horizontal components to get the net horizontal force, and the same for the vertical ones. And finally, using those net components, it calculates the overall strength of the net force, which ends up being 128 newtons,
Mm-hmm.
and its direction, which is 141 degrees from the axis they chose.
Okay, so you break it down, add it up, and then use the Pythagorean theorem.
Exactly. It's a really clear step-by-step guide to using this component method.
Cool. Cool. Before we move on, there's a test your understanding section about gravity acting on a crate on a ramp, figure 4.5. What's the main takeaway from that?
The important thing here is that when you choose your axes, especially on a slope, the force components might not line up with those axes. In this case, with the x and y axes, they chose both the x and y components of the gravitational force on the crate end up being negative.
Ah, I see.
It just shows that how you set up your coordinate system can change the values and signs of your force components.
So you have to be careful how you set things up. Okay, so we've got a good handle on what forces are and how to combine them. Now let's move on to Newton's first law of motion. The chapter starts by asking, what happens when the net external force on an object is zero? What does Newton's first law say about that?
Well, our everyday experience might make us think that things just naturally come to a stop.
Mhm.
If you want something to keep moving, you got to keep pushing it.
Mm.
But Newton's first law says something different.
Okay.
A great example they use is a hockey puck.
Okay.
On a rough surface like a tabletop, it stops pretty quickly.
Yeah.
On ice, it slides much further. And on an air hockey table where there's almost no friction, it keeps moving forever. Figure 4.8 shows this.
So it's friction that's slowing things down.
Exactly. Friction is the culprit.
Yeah.
If we could get rid of friction completely,
Right.
then Newton's first law tells us an object will keep moving at the same speed and in the same direction forever. And that speed could be zero, meaning it's at rest, or it could be some other number, meaning it's moving at a constant speed. In both cases, the acceleration is zero.
So once something's moving at a certain speed and in a certain direction, it doesn't need any more force to keep going. That's like inertia, right?
Exactly.
Yeah.
Inertia is this natural tendency of an object to resist changes in its motion.
Yeah.
It's like that classic example of shaking a ketchup bottle. You swing the bottle forward and then stop it suddenly, but the ketchup inside wants to keep moving forward.
Right, out of the bottle.
Exactly. And it works the other way, too. An object at rest wants to stay at rest unless some force acts on it.
Mhm.
It's like when you pull a tablecloth out from under some dishes quickly.
Uh-huh. They stay put.
Yeah, they stay put because of inertia.
Okay, so inertia is like resistance to change. But the first law talks about net external force. Why is it important to say net and external?
Because often you have lots of forces acting on an object, but they might cancel each other out. Take a book on a table. Gravity's pulling it down, but the table's pushing up on the book with the same force.
Right.
So the net force is zero and the book just stays put.
Stays on the table.
Exactly. Stays on the table. Which fits perfectly with Newton's first law. And a hockey puck sliding on perfectly smooth ice would have gravity pulling down and the ice pushing up, canceling each other out, leaving no net horizontal force to change its motion.
So it's the overall combined force that matters.
That's the key. It's not just about individual forces, but how they all add up together.
So then there's the idea of equilibrium. What's that all about?
Basically, an object is in equilibrium when it's either at rest or moving at a constant velocity. And Newton's first law tells us that happens when the net external force acting on it is zero. Equation 4.3 sums it up. S equals zero. So equilibrium means no net force.
Okay, zero net force means constant velocity, which could be zero.
Exactly.
Okay, now the chapter gets into inertial frames of reference. That sounds abstract. Why do we care about where we're looking from when we talk about motion?
That's super important because Newton's first law and all of Newton's laws only work properly in certain reference frames called inertial frames. Imagine you're on a bus and it suddenly speeds up. You feel like you're being thrown back even though nothing's actually pushing on you.
Right.
From your perspective on the bus, it looks like you're accelerating backward, for no reason,
Right.
and Newton's first law doesn't seem to apply.
Right.
That's because an accelerating bus isn't an inertial frame of reference.
Okay, so an inertial frame is one that's not accelerating.
Exactly. And for most everyday stuff, the Earth is a pretty good inertial frame,
Right.
but not perfectly because it's rotating and orbiting the sun.
Right.
Figure 4.10 in your source shows what you feel in accelerating cars and how objects tend to keep doing what they're doing relative to a truly inertial frame. So when the bus speeds up, your body wants to stay where it was compared to the ground.
So like if you're in a car and it slams on the brakes, you kind of keep moving forward relative to the road.
Precisely.
You kept moving forward.
Even though relative to the car, you're moving forward towards the dashboard. That's it. Exactly.
Yeah.
And the chapter says that any frame of reference that's moving at a constant velocity relative to an inertial frame is also an inertial frame. It's the acceleration between frames that messes things up. So when you're looking at motion, always think, is my perspective changing things? If you're accelerating, what you see might not be the whole story.
Gotcha. There's an example comparing a Porsche and a Beetle, both moving at constant velocities. Which one has a greater net external force?
You might think it's the Porsche since it's going faster,
Right.
but the key word is net. Both cars are going at a constant velocity, so they're not accelerating.
Right.
And Newton's first law says if something's not accelerating, the net force on it's got to be zero.
Ah.
So even though the Porsche's engine is pushing it forward, there must be an equal force from air resistance and friction pushing back.
Yeah.
So the net force is zero, just like the Beetle.
So the faster car is experiencing more forces, but they cancel out.
Yeah.
So the net force is still zero. Cool. And the test you're understanding for this section reinforces that idea. If something's moving at a constant speed in a straight line, the net force is zero.
Yeah.
But if it's moving in a circle, like a hawk circling, there's a net force because its direction is changing.
Right. That's an important point.
Yeah.
Just because the speed's constant doesn't mean there's no acceleration. If the direction's changing, there's still acceleration, and that means there must be a net force causing it.
Right. And they also talk about that common mistake in science fiction where a spaceship turns off its engines and just stops in space.
Oh, yeah.
That wouldn't happen, right?
Nope. Newton's first law says no way. If there's no friction in space once the engines are off, there's nothing to slow the spaceship down.
Right.
It would just keep going at the same speed and in the same direction forever.
Cool. Okay, so we understand the first law.
Right.
Now, what happens when the net external force is not zero? That's where Newton's second law comes in, right?
Right. Newton's second law tells us exactly what happens when there's a net force.
Yeah.
They go back to the hockey puck. If you apply a constant horizontal force to a counzip, it'll accelerate in the same direction as the force. Figure 4.Newton-C shows that.
Okay, so a net force causes acceleration. Seems intuitive.
It does. But the second law gives us an exact relationship between the net force, the mass, and the acceleration. It says that the acceleration is directly proportional to the net force. So if you double the force, you double the acceleration. Figure 4.44 demonstrates this.
Okay, and it also has to do with the object's mass, right? There's that idea of inertial mass.
Yes. For a given force, the acceleration is inversely proportional to the mass. So the heavier something is, the harder it is to accelerate it. Equation 4.4 defines inertial mass. It's basically the ratio of the force to the acceleration. So a really massive object has a lot of inertia.
So if I push a ping pong ball and a bowling ball with the same force, the ping pong ball will accelerate way more because it has way less mass.
Exactly. And that's what you feel when you pick things up. That heft is basically the inertial mass.
Cool. And then they define the Newton in terms of mass and acceleration.
Right. 1 Newton is the force needed to accelerate 1 kilogram at 1 meter per second squared. So 1 N equals 1 kilogeometer squared.
Okay, so that gives us a better idea of what a Newton actually means. They also talk about how you can compare masses by seeing how they accelerate under the same force.
Right. If you apply the same force to two objects, the ratio of their masses will be the inverse of the ratio of their accelerations. So you can figure out an unknown mass by comparing its acceleration to a known mass when you apply the same force.
That makes sense.
Okay.
Okay, so what's the formal statement of Newton's second law?
It says that if a net external force acts on an object with mass m, the object will accelerate in the same direction as the force, and the force is equal to the mass times the acceleration, if S equals in U, is equation 4.6.
That's a pretty simple equation for such a fundamental concept.
It is, and the chapter emphasizes that it's a vector equation. So the directions of the force and acceleration always have to be the same.
Gotcha.
And it's often helpful to use it in component form, like in equations 4.7, so you can break it down into x, y, and z directions.
Right.
And it's important to remember that we're only talking about external forces here. Internal forces within the object don't affect the overall acceleration. And this law only works for objects with constant mass, and when we're observing from an inertial frame of reference.
Okay, lots of things to keep in mind. Now, there's a really important point that they make that a lot of people get wrong. It's that mass is not a force.
Yeah, that's a big one. People mix that up all the time.
Why is it so important to understand that?
Because while mass is mathematically equal to the net force, it's not actually another force acting on the object. Acceleration is the result of the net force. The feeling of being thrown back in a car isn't from some force of acceleration. It's just your body's inertia. It wants to stay at rest while the car accelerates under you, as shown in figure 4.10a. Thinking of mass as a force can really mess up your understanding, especially when things aren't inertial frames. It's all about cause and effect. The net force is the cause, and acceleration is the effect.
Okay, I think that car example makes it clear. So the force is the cause and the acceleration is what happens because of it. The chapter mentions designing high-performance motorcycles as an application of Newton's second law.
Oh, yeah.
How so?
Well, motorcycle designers use Newton's second law to make their bikes accelerate really fast. To get maximum acceleration, they want to maximize the forward force from the engine while minimizing the total mass of the bike, and our lighter bike plus powerful engine equals faster acceleration.
Right, makes sense. More force, less mass equals more acceleration.
Exactly.
The chapter also works through some examples like the worker pushing a box. Example 4.4, what are the main steps there?
That example and the free body diagram in figure 4.17 show a really systematic way to solve problems using Newton's second law. The first thing you do is figure out all the forces acting on the box and draw a free body diagram.
Okay.
Then you choose a coordinate system. And finally, you apply Newton's second law in component form, flex, max, and pica-mise to figure out whatever you're trying to find. In this case, it's the acceleration of the box.
Right.
The example also shows how forces in one direction can balance out like the vertical forces of gravity and the normal force leading to zero acceleration in that direction, while the forces in another direction can cause acceleration like the horizontal applied force and friction.
Gotcha. And there's another example where a waitress pushes a ketchup bottle. Example 4.5. That one's cool because it uses both Newton's second law and stuff from kinematics.
Yeah, and that one you're given information about how the bottle moves.
Yeah.
Like its initial and final velocity and how far it travels. And you have to figure out the friction force. So first you use kinematics equations to calculate the acceleration.
Uh-huh.
And then once you know the acceleration, you can use Newton's second law to relate that to the net force, which in this case is just the friction force.
So you figure out the acceleration from how the bottle's moving and then use that to find the force.
Exactly. It's a good example of how different parts of physics connect.
Cool. The chapter also mentions other units for force and mass like dynes, pounds, and slugs. Do we need to worry about those?
Well, the SI system is the standard in science, with newtons for force and kilograms for mass. But it's good to know those other systems exist, like the CG system and the British system. Table 4.2 summarizes them, and figure 4.1 times shows them visually. You might see those units in older stuff or in engineering.
Okay.
The book gives you conversion factors if you need them, but for most physics nowadays, it's all SI.
Good to know.
Yeah.
And finally, the test your understanding section for this law gives you a scenario where you have to rank accelerations based on forces and masses. It's a good way to check if you get the main idea.
Yeah, it helps make sure you understand that acceleration is proportional to force and inversely proportional to mass.
Okay, so we've covered how force affects acceleration. And now let's talk specifically about mass and weight. The chapter makes a big deal about how they're different, even though people use them interchangeably all the time.
Yeah, that's super important to understand. Mass is all about how much stuff an object has.
Right.
It's like how much it resists being accelerated when you apply a force.
It's inertia.
Exactly. It's inertia.
Yeah.
Weight, on the other hand, is the force of gravity pulling down on the object.
Okay.
So your mass is always the same no matter where you are, but your weight changes depending on how strong gravity is.
So my mass would be the same on Earth and on the moon, but I'd weigh less on the moon.
Exactly. Because the moon's gravity is weaker,
Makes sense.
and they use a falling object to show the relationship. When something's falling near the Earth, it accelerates downward at about 9.8 meters per second squared, and that's because of gravity. It's weight. And Newton's second law says that weight is equal to the mass times the acceleration due to gravity. WA equals MAG. That's equation 4.8. And equation 4.9 shows it as a vector equation, so we know it's pointing down.
So weight is a force measured in newtons, and it's directly related to mass, which is measured in kilograms.
Exactly.
And the thing that connects them is real or the acceleration due to gravity.
That's right. And figure 4.20 shows that the weight force acts on an object, whether it's falling or just sitting there, Even when a book's on a table, its weight is pulling down and the table's pushing up with an equal force to keep it from falling.
They also point out that G isn't actually constant everywhere on Earth.
Right. It changes a little bit depending on where you are.
Hmm.
And on other planets or moons, it's way different. Like on the moon, G is only about 1.62 meters per second squared, which is about 1/6 of what it is on Earth.
Wow.
Figure 4.22 shows that. So an 80-kilogram astronaut would weigh way less on the moon, even though their mass is the same.
That's a huge difference.
It is.
Yeah.
It really shows that mass and weight aren't the same thing.
So if mass is about inertia and weight is a force, how do we actually measure mass in everyday life?
Most scales actually measure the force pushing down on them, which is usually related to weight.
Right.
And then, assuming the Earth's gravity, they convert that force into a mass, reading in kilograms or pounds.
Mm-hmm.
So we're indirectly measuring mass by measuring weight.
Oh, okay.
Balances like the one in figure 4.23 work differently.
Hmm.
They compare the weight of an unknown mass to the weight of known masses. So they're directly comparing masses.
Okay, cool. They also mention gravitational mass versus inertial mass and how experiments show they're the same. Is that something we need to get into right now?
Not really.
Yeah.
For now, it's enough to know that even though they sound different, gravitational mass, how mass interacts with gravity, and inertial mass, how mass resists acceleration, are basically the same thing.
Okay, good to know. And they're really careful about using the right words for mass and weight. Like, you shouldn't say, this bag weighs 5 kilograms.
Right.
You should say, this bag has a mass of 5 kilograms.
Right, because kilograms is mass.
Exactly.
And then you can figure out its weight
Yes.
by multiplying by g.
Exactly. It's important to use the right words in physics so everyone understands what you mean.
Okay, conceptual example 4.6 with the falling coin.
Okay.
Figure 4.21 points out that when something's falling, the only force acting on it is its weight, which causes it to accelerate down at g.
Right. And that acceleration is constant no matter how heavy the object is, as long as we ignore air resistance. And example 4.7 about a braking truck shows how to figure out the mass of the truck from its weight and then use Newton's second law to find its acceleration.
Yeah, this is a good example of how you might have to work backwards from weight to find mass before you can use Newton's second law.
Gotcha. And the test your understanding for this section emphasizes that gravity doesn't care if something's moving or not.
Yeah.
An object at rest and an object falling will both feel the same gravitational force.
Exactly. Gravity depends on the mass and where the object is not, whether it's moving or not.
Okay, cool. We're making good progress. Now let's get to Newton's third law of motion. This is the one that everyone knows as, for every action, there's an equal and opposite reaction. What's a more accurate way to say that?
The more precise way is this. When two objects, let's call them A and B, exert forces on each other, the force from A on B is equal in strength and opposite in direction to the force from B on A. That's equation 4.10.
So if I push on a wall, the wall pushes back on me with the same force,
Exactly.
just in the opposite direction.
Exactly. Those two forces are called an action-reaction pair. And it's really important to understand that those two forces always act on different objects. Figure 4.24 shows this really well.
So the action and reaction don't both act on the same object.
Right, they act on different objects.
Right.
If they acted on the same object, they would always cancel each other out and nothing could ever accelerate.
Right, because then the net force would always be 0.
Exactly. The chapter even warns you not to include both forces from an action-reaction pair in the free body diagram of a single object.
Because when you're analyzing something, you only care about the forces acting on that one thing.
That's right.
So like if you're analyzing a soccer ball being kicked, you'd include the force from the foot on the ball,
Yep.
but not the force from the ball on the foot.
Exactly. Because that force doesn't directly affect the ball's motion.
Gotcha. And Newton's third law applies to all forces, right?
Yes. All kinds of forces, both contact and long range. Like even gravity. The Earth pulls down on a tennis ball, and the tennis ball pulls up on the Earth with the same force.
Even though they're not touching.
Even though they're not touching.
It's weird to think that a tiny tennis ball is pulling on the entire Earth.
I know. It's kind of mind-blowing.
Huh.
But the effect on the Earth is tiny because it's so much more massive.
Right, because M.
Exactly. Even though the forces are the same, the accelerations are different because of the different masses. The Earth barely moves while the tennis ball falls towards it.
Okay. Conceptual example 4.8 asks about pushing a car. You push on the car, and the car pushes back on you.
Right.
Does that relationship change if the car starts moving?
Nope. Newton's third law is always there. As long as you're pushing on the car's pushing back on you with the same force. It doesn't matter if the car is moving or not.
Okay. And conceptual example 4.9 is about an apple sitting on a table, figure 4.25.
Yes.
It shows that the apple's weight pulls it down and the table pushes it up,
Right.
and then it asks about the reaction forces.
Right, so the reaction to the apple's weight is the apple pulling up on the earth. And the reaction to the table pushing up on the apple is the apple pushing down on the table. The important point is that the apple's weight and the normal force from the table are not an action-reaction pair.
Why not?
Because they both act on the same object, the apple. To be an action-reaction pair, the forces have to be from two objects acting on each other.
Gotcha. And then there's conceptual example 4.0 with a stonemason pulling a block with a rope, figure 4.26. That one talks about tension.
Yeah, that example breaks down the situation into all the action-reaction pairs. It shows that forces on the same object, even if they're equal and opposite, aren't third-law pairs. And the tension in the rope comes from the forces between the mason and the rope and between the rope and the block.
Okay, and then there's that Newton's third law paradox where the stonemason pulls the block and the block moves, but the mason might not.
Right, that one can be confusing. But the key is to remember that each object's motion depends on the net force on that object. The block moves because the tension in the rope pulling it forward is stronger than the friction holding it back. But the mason might not move because the tension pulling him toward the block might be balanced by the friction between his feet and the ground.
Ah, so the block moves and the mason doesn't because they have different net forces acting on them.
Exactly. The third law just tells us about the forces between the mason and the rope and the block.
Right. Okay. And they also talk about a massless rope. What's that all about?
That's just an idealization where you pretend the rope has no mass.
Yeah.
It makes things easier because you can assume the tension is the same everywhere in the rope. So the force the rope exerts on one object is the same as the force the other object exerts on the rope.
Gotcha. Makes it simpler.
Yeah. And the test your understanding with the mosquito hitting the car is a classic example of the third law.
Right.
The forces are equal, but the effects are totally different. The car basically doesn't even notice while the mosquito gets squashed. Yeah, that's because of Newton's second law.
Right. The forces are the same, but the accelerations are different because of the different masses.
Exactly.
Okay, we've covered all three laws. The last section is about free body diagrams. Why are these diagrams so important for using Newton's laws?
Free body diagrams are essential for visualizing the forces on an object. Remember, Newton's laws apply to one object at a time, and only the external forces acting on that object determine its motion. Feth S equals may S.
Right.
A free body diagram is just a drawing where you isolate the object and show all the forces acting on it as arrows. Figure 4.17, 4.18, 4.20, and 4.25a are good examples.
So you take the object out of the picture and just draw the forces as arrows.
Exactly. And you never include both forces from an action-reaction pair in the same diagram.
Right, because you only care about the forces on that one object.
That's it. And if you have multiple objects, you need a separate diagram for each one.
Yep.
In figure 4.26c and figure 4.27.
Right, they show some examples from real life in figure 4.29.
Yeah, like a runner, a falling player, and a swimmer. Those examples show how each arrow represents a force on the person from something else in their environment, like the force from the starting block on the runner's feet or the force of gravity on the falling player.
Right.
And for the swimmer, it's the force of the water pushing them forward, which is a reaction to them pushing the water back.
Okay, and they also warn against drawing forces that don't exist.
Yeah.
Like that force of acceleration.
Exactly. For every force you draw, you should be able to say what other object is causing that force.
Yeah.
If you can't, it shouldn't be in the diagram.
Right.
Figure 4.28 about walking is a good example. The force that makes the person move forward is the force from the ground on their feet, which is the reaction to them pushing back on the ground.
So free body diagrams are all about showing the external forces acting on a specific object.
Exactly. And that's the first step in using Newton's laws to analyze how things move.
Cool. So we've learned a lot in this deep dive. We've talked about force as an interaction and a vector. We've gone through all three of Newton's laws, and we've seen how important free body diagrams are.
It's amazing how Newton's laws can explain so much about how the world works.
They really are fundamental. And for you listening, try to pay attention to the forces around you. Think about something simple like riding an elevator. What's happening to you when it starts going up or stops? What forces are acting on you in those moments?
It's fun to think about.
It is. And understanding these basic ideas opens up a whole world of more complex physics.
For sure. It's the foundation for understanding how everything moves.
So keep exploring and keep asking questions.
Yeah, keep learning.
Thanks for joining us on the deep dive. Until next time, keep digging deeper.